Welcome to the small and cozy Acorn Room, and thank you for moving up to the front. We're working with one microphone today, so for the comfort and courtesy to our Zoom members, please please find a seat up in the front so that they can hear what's going on. We will hold questions from Dr. Zimmerman until the end. Zoom folks, please put your questions in the chat. We're not going to monitor it as we go. If you're having any trouble with the technology, could you please just unmute yourselves and holler out that we've got an issue? That way we can see if we can do something to fix it. You know that the curriculum folks are working really hard to try and repair all of the Zoom challenges we've been having. Welcome and come on up to the front, please, if you don't mind. So a couple of very short announcements. One is, it looks like your plastics recycling program is already off to a gangbuster start. This is for recycling all of your soft plastic that does not go in the county recycling bin. And the category is anything that doesn't crinkle, and anything that stays crunched when you crunch it can go in. So that's your bread wrappers, your frozen vegetable wrappers, Amazon bubble wraps, Publix bags. And Kristen's been very good about bringing me a bag of garbage every week. Kristen, from now on, you can actually put it in your own trash room. So kudos to your colleague, Nita Beckman, and to Rebecca Snowden for getting that going. The other announcement that relates to climate and climate engagement is next Tuesday. And you'll probably see an announcement. I'm not sure where Kathy Subak puts it, but you'll see an announcement that Don Smith, one of your colleagues, has asked to start a climate movie club. And next week, I'll be helping facilitate a conversation after watching a film called Sinking Cities. If you've never seen it, kind of dramatic. It deals with Miami and New York, cities many of you are familiar with, as well as Tokyo and London, also cities you may be familiar with. So, and then two more business announcements. I've put because this is my last class with you, it's my last time to beg you to fill out Right to Clean Water constitutional amendment petition forms. So they're on the chairs. If you need a pen, I'll make sure one gets circulated. And if you have not already said, yes, I would like to be on the Ellen's Clio email list, I'm going to pass around the clipboard once again. If you don't remember if you signed it, sign it again and I'll clean it up. Clio, people keep saying, well, what's Clio stand for? And I keep going, right, I need to remember to tell you that. It stands for Climate Leadership Engagement Opportunities. And my job is to help people who want to do something. And the Science Committee, thank you for your support yesterday, Pushpa. The Science Committee is allowing me to introduce, a year from now pretty much, a pilot project through the Thomson Earth Systems Institute at the University of Florida called Community Action Project Engagement. So you'll be hearing from me, but probably not for a while. And that takes care of the business things. I'll start this around and you can just pass it around. We're closing out this session with one of my most favorite professors at the University of Florida. This is Andrew Zimmerman, who I met through his engagement with my synagogue on a climate action plan. Yes, my synagogue has a climate action plan, and Dr. Zimmerman helped craft it. But what he does for his paying job is he's an organic geochemist and a professor of geological science at UF, and he teaches classes in climate change, oceanography, sustainability science, and geobiology. He actually has a very unique specialty, and he did a wonder for us several months ago. He studies carbon cycling, particularly carbon produced by fires, and he's looking at how did past human activities lead to global change. It's called biochar, and I don't know if it got recorded, but it's really interesting how you can make charcoal without putting carbon dioxide in the air and how that charcoal will suck carbon dioxide out of the air. But that's not today's topic. today's topic is how do you know what to believe? Because there's a lot of information out there. So he's going to look at evidence and uncertainty when we talk about climate change. And we have permission to refer to Dr. Zimmerman as Andrew, so it's my pleasure, Andrew, to welcome you.
Thank you. So do we want the lights on like this or turn them off? Is this okay then? Arc like this? Okay. So yes, so Ellen gave me the title, How Do You Know What to Believe? Although, whoop. There we go. Okay. Although really, I think a better title might be, Why Do We Believe What We Believe? Since this is a climate change um, lecture series, I guess. And really, you know, this lecture probably should have been the first one in this series because it's sort of, you know, all the sort of background information about climate change. But I couldn't do that because I was out of town until now. So now you'll get why do we believe what we believe. So to start off, I like to start off with just, you know, what do people believe? And you know, I could take a poll here, but I'm presuming that we're in this climate change symposium because we believe climate change is happening. But as far as the American public goes, you can see it's been increasing since about 10, 15 years ago from around 45, 50%. It's up to 60% of Americans would say that, yes, global warming is happening and it is human caused, which is essentially the theory of global warming. So we're up to 60%. And another question that has been asked Americans is, do you think most scientists are convinced that global warming is happening and human caused? And that has really come up from around 30% in 2010 to around 60% now. But there's still, you can see about 20, 25% of Americans that think that there is a lot of disagreement among scientists about whether climate change is real. And the truth of it, if you take polling as truth, is that about 80% of scientists would say that climate change is happening and human caused. But if you go from all of scientists up to climate scientists and then up to actively researching climate scientists, you get up to 97% of agreement of global change happening. So it's there's a strong consensus. And another sort of reflection of that consensus is, I'm sure you've heard of the IPCC, or the Intergovernmental Panel on Climate Change. But a lot of people don't realize what they are. They're really a group of scientists that are assembled not to do research, but to look at the literature on climate change and to sort of assess what that literature is telling us. And that literature, that peer-reviewed literature is also another form of scientific consensus besides polling. And back in about 10 years ago, they released these assessment reports every 6 years. And in 2014, they said it was virtually certain that temperatures are rising, according to the literature, extremely likely that this increase is because of increased greenhouse gases. And they also have other assessments about other things, such as is sea level rising. And these terms, virtually certain, extremely likely, they're actually specifically related to probabilities, and that really comes from how much of the literature agrees and what kind of evidence is presented in the literature, and being very careful about stating certainties about different aspects of the climate change science because of this skepticism that is out there. I find it interesting that in the most recent assessment report, which was 2021, assessment report 6, they changed it. They're no longer saying virtually certain or extremely certain. They're saying unequivocal, which means they're kind of getting away from the scientific terminology about certainty to say that there's really no argument among the scientific community that it's warming, it's widespread, it's affecting all different aspects of the Earth, from the atmosphere to the oceans. And, even with that, even though the scientific community is is completely certain, it's still, you remember, about 20% of the public saying that they don't think it's real. And another, well, this is just an interesting one on the side. What percent of Americans say that addressing climate change should be a top priority of the U.S.? What do you think it is? 20%, 40, 80, higher, 80, 90, 60? I'll show you the answer there. So it's 40% of Americans, okay? But this is really interesting. For Democrats, it's about 80%. And for Republicans, it's about 20%. And that's where you come up with the average of 40%. And this is all different issues, which, clearly there are differences in Democrats versus Republicans, but there's no bigger divide, right? Among these two political parties as to the importance of dealing, compared to any other issue. And so that's interesting. And, so why is that? And there's still, there's a lot of different reasons. I mean, one of them is, you could say, political and cultural affiliation. That is where you believe what everybody you're associating with believes, and of course, misinformation. And I would say one of the problems is that, not if you live in Florida, but if you live in most places in the US, it still gets very cold in the winter, and we have big snowstorms. And so there's sort of, direct evidence in people's experience, maybe, that it's not, global warming is not happening. And that, I think, comes from a misconception between the difference between weather and climate, right? Weather is what's happening in the atmosphere today, or maybe, generally this summer, whereas climate is really a 30-year average. And it varies. Different climate scientists use different numbers, but 20 to 50 years, but a 30-year average. And I don't think, people cannot directly experience a change in a 30-year average temperature of 2 degrees. And so you really need to be looking at data if you're really going to be convinced one way or another. And that is really all the preface to this talk, which is a talk that I give to all my classes, and sometimes I visit other classes and go to different communities, public schools, retirement communities, and really just present, like, okay, here is the evidence for that the climate is changing. Here is the evidence number two. I'm going to talk about what's the evidence that humans caused it. And I think it's important that we understand, of course, there's always some uncertainties. What are those uncertainties? And I may or may not get to last one, just some of the arguments and counter arguments that people have. But the most important thing is number one and number two here. Okay, so again, a lot of, even people like you are maybe convinced, yes, climate change is real, but maybe you don't have right at your fingertips, what is exactly the evidence? And so that's really what this talk is about. Okay, so first, evidence that climate has changed. And mostly this is about global warming. So average Earth temperature has changed. And so these are the 6 lines of evidence that I would say are the most important. One is what I call theoretical, meaning our understanding of how the climate works and the greenhouse effect. Another is the short-term record, and by instrumental record I mean thermometers. Long-term record, the geological record, changes in ice coverage, changes in extreme meteorological events. And this last one, most people probably haven't heard of, is changes in the upper atmosphere, or the profile of temperature in the atmosphere. Okay, so first of all, on this greenhouse effect or theoretical evidence, you have to understand a little bit about what really sets the temperature of the planet, or what's called the energy budget. And so, all of the energy of going into our atmosphere comes from the sun, and it's emitting shortwave radiation, most of which passes right through the atmosphere. Some is reflected back to space, but it warms the Earth. And then the Earth emits, after it's warm, it emits long wave radiation. And it's really this long wave radiation that is then warming the atmosphere. Okay, the sun does not warm the atmosphere from above, it's the Earth warming it from below, which is why when you go up mountain, it gets colder and colder. You're kind of going further and further away from the mass of the Earth. Okay, the next observation is one made all the way back in 1859 by John Tyndall. And this is the observation that certain gases absorb long wave radiation. And so these gases, we call the greenhouse gases, include water vapor, carbon dioxide, methane, and some other ones. And by absorbing that radiation, that really means it starts those molecules vibrating, and then they emit heat. And so you can see here in this picture right in the middle at, what is this, 700 centimeters. This dip is CO2 absorbing a lot of that long wave radiation, but also water vapor on both sides is a strong greenhouse gas. So this, for a long time, this has been known, and even, let me just go back a second, and it was even proposed not much after this that, okay, well, we're burning coal and fossil fuels and we're increasing the CO2, that should warm the planet. So this whole greenhouse theory is from the late 1800s, not at all a new idea. And so that's again, this is just another picture of it. Sun warming the Earth, Earth warming the atmosphere. And in a sense, it operates like a greenhouse, right? That energy cannot escape to space not because there's a glass window like a greenhouse, because there's these gases that don't let that energy escape. And of course, it's a natural thing. There's always been these greenhouse gases in our atmosphere, and those concentrations have changed. So for example, if we didn't have CO2 water vapor in our atmosphere, we might be like a planet that this one's Venus. I think this one's Mars. We'd be minus 17 degrees Celsius if we didn't have those greenhouse gases. And we could have a whole lot of greenhouse gases and be 467 degrees Celsius like Venus. And it's really just a lucky thing that the Earth has the perfect amount of greenhouse gases. We haven't always had that perfect amount, but and we have the average temperature of 15 degrees Celsius, which is comfortable for life. So greenhouse gases, basically regulate the temperature of the planet. And this is a curve that is called the Keeling curve. It's really one of the most famous graphs in environmental science, which a scientist started measuring CO2 on top of a extinct volcano in Hawaii, Mauna Loa. And the reason for doing it in Hawaii is because you're far away from any cities and forests and things that, it's very well mixed out in the ocean, and also way up high, the atmosphere is well mixed. And shows that since 1960, we've gone from CO2 of 320 parts per million to today, 426. And that really is today. I just looked up the CO2 concentration, and that's a 40% increase. Do you know what these wiggles up and down every year are? Can anybody guess why it goes up? It actually goes up every winter and down every summer. Not reflection. what happens so it's actually in the northern hemisphere summer, plants grow and absorb CO2, right? Take it out of the atmosphere. And in the winter, plants die and release that CO2. And it's the northern hemisphere because we have much more continent and more plants that are, in that. So yeah, so we've had a 40% increase. And so this is what I mean by theoretical evidence. Theoretically, if you increase a greenhouse gas by that much, we should see some warming. And we also have the record of what CO2 has been doing over the last million years by drilling ice cores. We've now drilled them in Antarctica and we've drilled them in Greenland. And we know that during a glacial period, the CO2 goes down. Interglacial period, it goes up. And so we've had these glacial, interglacial cycles. And, then came out of the last ice age and it stabilized. But then right in the last 150 years, we've gone up to this 420. And so this also is evidence, this CO2 is related to temperature. And what's really scary is, we're already outside of this range of natural variation over the last million years. Where we're headed, if we keep on business as usual, by the end of the century, it's estimated about 900 parts per million. So even further. Okay, so that's what I call theoretical evidence. Increased CO2 should increase temperature. Next is the instrumental record, meaning thermometers. And this is a map showing where we have all our meteorological stations. And it also shows how long those meteorological stations have been measuring the temperature in that one location. And so you can see that, the United States, Europe, maybe Japan, more early industrializers, so we have longer temperature records. We have, they're kind of spread over land. We have very few out in the ocean, obviously, because there's no islands in a lot of places. And so, how do we come up with this global average temperature that we keep talking about? Well, you can't just average all these temperatures, right? I mean, because then you'd be heavily weighting United States and Europe, and you wouldn't be accounting for a whole large parts of the world that don't, or this location maybe should be more heavily weighted because it's accounting for a larger area. And so it really takes a whole team of scientists to use models to take all this data and make it into what we're going to call the global average temperature. And there's really three groups that are famous for doing this. NOAA in the US, NASA in the US, and the United Kingdom Meteorological Office. And so, how they assemble all that data is kind of an art. But what I want you to see is that all of these groups working independently, and now they're plotted together on the same graph, really came up with the same record. And so this shows, that since pre-industrial times, we've had an increase of 2.4 degrees Fahrenheit or 1.4 degrees Celsius. And you can also see that most of this temperature increase really happened since about the 1980s, really. So we've had an acceleration of temperature increase. So that's the of course, very strong evidence that the globe is warming. And another way to look at this instrumental record is, when we have record temperature, record average years for average temperature. And when I started giving this lecture back in about 2010, I could say something like, 4 out of 10 of the hottest years were in the last decade. But now we're up to, I can say all 10 of the hottest years have occurred in the last 10 to 15 years. And all 8 of the last years were the hottest years. And last year was the hottest year with an average of 1.7 degrees above global average temperature. And so it doesn't look like this record setting is stopping. We truly are into unprecedented territory of global average temperature. And by the way, so we don't have as long records for the ocean, but we're starting to have all these floats with thermometers measuring the upper layer of the ocean, because that's the layer that's interacting with the atmosphere. And these are from sort of fossil records, but we now have actual instrumental records showing that the ocean is also warming, and we're setting record temperatures in the ocean as well. I thought you might like to see the Florida data. This is for average over the state of Florida. And if you look at about any state in the US, you're going to see something like this with, we do have very cold years and we do have very warm years, but you can see something starting to happen around the 1990s where almost every year is starting to be above average temperatures. So that's happening here too. Okay, now for the long-term record, this is something geologists do. We have all different what we call proxies, meaning things that we can measure. Not thermometers, but things we can measure that we can track back to temperature. Things like the chemistry of ice in an ice core, tree rings, the type of pollen we find in sediment layers of a lake. And putting all of those together, see, these are all different records. And this is the last 1,000 years. We see that, there was this medieval warm period, got a little warmer in the middle of the last century, but something different is happening in the last 100 years or so. But the records are, most of this work has been done in the Northern Hemisphere because that's where most scientists are, where most land mass is. And so it's not maybe truly global. You can argue with it for that reason, but still. But the ice cores that we've collected is one of the stronger types of geological record. And I actually already showed you this temperature record and CO2 record, and this is a geological record showing a strong correlation between CO2 and temperature, interglacial, glacial, and something's happening that's not just, so this was the CO2 is a lot higher now, and also the temperature is starting to reflect that higher CO2. Okay, so we talked about theoretical, we talked about instrumental and geological record. Ice cover is another type of evidence that I think is a strong type of evidence, if we see a change in, any of these forms of ice, like how much snow in the winter, sea ice sheets, glaciers, because ice kind of melts. If it's a large mass of ice, it forms very slowly when it's colder and it melts very slowly when it's warmer. And so it's also kind of a recorder of long-term conditions in that sense. And you can find a lot of stunning pictures from single locations like this. This one is from Glacier Bay in Alaska, a photo that was taken in 1940 on the left, and one in the same location more recently on the right. So this is showing the recession of a glacier. And all over the world, say 50 years ago, you would find glaciers advancing and glaciers receding. But at this point, we're starting to see more, most of them receding. So places like in Alaska here, this is a picture from the Cascades in the state of Washington. But if you want to really have to put all the glacial data together, this is done by the Glacial Monitoring Service that tracks 140 glaciers worldwide. And what this shows is that since 1880, 1880, about equal numbers of glaciers were gaining mass and losing mass. And now the net is greater and greater, losing glacial mass. Sea ice, most of the sea ice is in the Arctic Ocean, and back in from 1880 to 2010, this red line on the left is showing the average, what is that, maximum, medium, average September sea ice extent, whereas now we're seeing much less sea ice. But the most ice in the world is found on ice sheets, right? Greenland and Antarctica. And how do you measure how much melting there is of an ice sheet? The way we do it is to fly a plane over those ice sheets that has a gravimeter, meaning measuring the gravitational pull of the Earth plus that ice. And doing that again, we've only started doing that since about 2000. And you can see that both in Greenland and Antarctica, over the whole continents, we're losing more and more mass of that ice. And of course, that's very concerning. Well, both glaciers and the ice sheets, because that's what is melting and adding to sea level. And then one last type of ice is permafrost. That is ice that is in the soils of the at high latitudes, and you can see this map of permafrost area shows a stunning decrease over time, over the last century. You know, and also just these really stunning images of large large collapse of areas collapsing. This is from Siberia, showing, you know, instability overall. Okay. Number 5 is changes in extreme meteorological events. And by extreme meteorological events, we mean droughts, hurricanes, floods. And this is a lot harder to have good data showing a trend because, you know, unlike temperature that is measured every day, all day in 1,000 locations, these are events that don't happen very often and not in a lot of locations. And so it's harder to see a trend. It takes longer to see a trend. But the science is getting better and better about using this kind of sparse and extreme data to see trends. But one type of extreme weather, you could say, is just a record temperature, record high temperature. And back in the 1950s, if you look at all meteorological stations over the US, back in the 1950s, there were about an equal number of record highs and record lows being set on any, over any particular year. Whereas now we're setting twice as many or 3 times as many record highs versus record low temperatures. So we're getting more extreme temperatures only on the hot end, fewer on the cool end. Another trend we're seeing is heavy precipitation, which has also been predicted because you have warmer atmosphere, you evaporate more moisture, and so it comes down in bigger episodes. And it used to these extreme rain periods are getting more and more frequent. And I thought I would show you some data for Florida. This is the most data in any slide, but I looked up the data for Florida on number of very hot days, and it doesn't look like a trend there, but it does seem like we've had a decrease, the bottom left so a decrease in the number of freezing nights. We've had a very big increase in the number of very warm nights. And we've had, hard to say any trend in the number of heavy precipitation events. So again, because we're only looking at one location, have less data that we can work with. But at least, less, and I've had people who have been in Florida a long time tell me that, yes, they've noticed that there's less freezes and the nights seem to be warmer. That's something that you felt is happening? Okay. Um, and another type of heat wave is a marine heat wave. And that is something that we're also seeing increases. And this is also of a lot of concern because there's a lot of organisms in the ocean like coral that depend on specific temperatures for their body, their reproduction or their body chemistry. And so that's a big concern. Okay, so if you go back to the IPCC reports, um, they have statements, again, using these terms that have very specific meanings. Very likely that the number of cold days and nights has decreased. Very likely the number of warm days and nights has increased. Very likely an increase in heat wave frequency. Whereas, we have less confidence about events that occur less often. So low confidence that there's a trend in how many floods we're seeing. Low confidence in any change in hurricane activity, and similar for droughts. Okay, now that last line of evidence I mentioned has to do with using satellite, measuring the temperature of the upper atmosphere using satellites. And what they're recording is a decrease in temperature of the upper atmosphere. And that actually makes sense if you're absorbing more heat in the lower atmosphere, you'd expect there to be less heat in the upper atmosphere. And I think this is actually a pretty strong type of evidence because, the atmosphere is very well mixed out when you get into the upper atmosphere and also recording a global signal. And so this trend really of cooling in the upper atmosphere does imply warming of the lower atmosphere, assuming that the sun hasn't changed, which it does actually change a little bit. Okay, so that's the evidence that it has warmed. What is the evidence that humans have caused this warming? In other words, okay, CO2 in the atmosphere has changed, but do we absolutely know that that came from humans? The lines of evidence for that, what I call hockey stick curves, something about a match of CO2 and how much fossil fuels were burned, the chemistry of the CO2 in the atmosphere, and models, computer models, which I will explain each of these. Okay, so first of all, a hockey stick, as you can imagine, is a curve that does this, right? Looks like a hockey stick. And we've already talked about CO2 as being a hockey stick, with that curve in the hockey stick being at the start of the Industrial Revolution, 1850s or so. Methane, another greenhouse gas, and nitrous oxide, those are both hockey sticks. However, I mean, if you look at any kind of a contaminant, DDT or lead, mercury, there's all are going to be hockey sticks doing the same thing because, industrial processes release all these contaminants. So for example, sulfate aerosols, which is also released when we burn coal, has that same hockey stick, but those aerosols actually cool the atmosphere by reflecting sunlight. So it's, hockey sticks you can't use a hockey stick alone to say that, human attribution. But remember also that another hockey stick that matches the hockey stick is the temperature itself that we get from our geological record. Okay, so how do we attribute that CO2 absolutely to humans? Well, one way we can do it is by looking at all the, starting with the Industrial Revolution, we started burning coal, and then we switched more to petroleum. Then we're switching in a big way to natural gas. And if you add up all that carbon, forms of carbon that were burned, you can pretty much match it to how much increase of CO2 in the atmosphere there's been. And you might say, well, how do we really know how much coal, how much petroleum was burned? Well, it's not actually that hard if you consider that most of it comes from, the US, Canada, a few European countries, and China, and you would be, and to some extent, Russia and Australia, you'd be making up for a large majority of it. So you really don't need that many records to come up with that match. Another way to match it is by looking at the isotope signature of the carbon in the CO2. So you've heard of carbon-14 dating, right? You find a mummy and you can look at the ratio of C14 to C12 and say how old it is. Well, we can do the same thing with CO2, with the atmosphere. And say for the atmosphere in 1700, we have to use some bubble of gas that was trapped in the ice, or maybe somebody put a cap on a bottle and then we open the bottle now. And what we find is that the atmosphere, the carbon, is getting older and older and older and older. Why would it be getting older and older? Because we're burning fossil fuels, right? Fossil fuels are called fossil fuels because they're fossil. They were formed 100 million years ago. And so when you add that CO2 to the atmosphere, it makes all of that carbon get older. And so that too is another way to attribute that increased CO2 to humans or burning of fossil fuels. Okay. As far as climate models go, these are very complex things because the climate is very complex. I showed you this sort of simple sun coming in and what happens to that energy, but that energy moves around. Some is released when it evaporates something or when it rains, or it moves over land. So there's a lot of different components. And so we have these very complex climate models. And the main point I want to make is if you run your climate models forward in time without that little extra bit of CO2. Okay, so remember we said 40% increase in CO2, but it's only going from a very small amount, like 300 parts per million, to 425 parts per million. So does that CO2 really have a big effect? Well, if you run your climate model without that 40%, then the results of the model shown in blue not match the temperatures we've observed in black. However, if you add that little bit of CO2, then our climate models in red are matching the observation. So that's why climate models are really so important. I mean, they are really the key evidence that attributes, that increase in CO2 to that amount of warming that we've seen. Okay, so so that's the first thing. It links the warming to the greenhouse gas, but also this is important because our models can, match the observations. It shows that we understand climate well enough to now use them to predict into the future, right? If we keep burning more CO2, how much more warming will we see? And I'm going to skip that. So that partly does relate to some of the uncertainties, which I'm going to go through a little quick. Okay, so because we talked about some of the uncertainty is what caused the warming of the past. Of course, the big uncertainty is what humans are going to do in the future in terms of releasing more CO2. What is the sensitivity of the climate to that? What we're going to do in the future? We're uncertain about what are we're talking about global conditions, but what's going to happen in, this region or that region. We talked about some of the uncertainties about extreme meteorological events. There's other things that our models don't necessarily account for, feedbacks and tipping points. And then finally, okay, so we do have a change in climate. What will the effects of that be? Okay, so first, as far as humans, we can't really predict what's going to happen with technology and burning of fossil fuels. And so we have different inputs we put into our model, like a business as usual input, or we're going to get our act together right away. This is called strong mitigation. Or maybe we're going to develop technologies mid-century. that will start decreasing our fossil fuel use. And it really matters. This is just showing, what by the temperatures at the end of the century is strong mitigation versus business as usual. Business as usual gets us to, I'll give you in Fahrenheit, 20 degrees more Fahrenheit, higher temperatures at the poles um, versus, say, an average of about, 5 degrees Fahrenheit. Whereas we only see a bit more warming if we mitigate right away, stop releasing fossil fuels. But even with these two scenarios, this is strong mitigation and business as usual, there is uncertainty. It's about plus or minus half a degree or plus or minus 1 degree in terms of the temperature we end up with at the end of the century. And that's because of our not complete understanding of the climate. And so these are all the different models people have come up with. And so that's the uncertainty. However, and in terms of local and regional climate, we do have this understanding that generally speaking, more warming over land than the ocean and more warming at higher latitudes than lower latitudes. But you can see that, if you're here versus right here, there's a lot of uncertainty in terms of each specific location, in terms of just temperature, let alone precipitation, flooding or hurricanes and things like that. Generally, you could say our models tell us that wet places are going to get wetter and dry places getting drier. So, for example, we already have plenty of rain in the Amazon. It's going to rain more, but in, say, the desert Southwest, it's going to get drier. But this is pretty uncertain because of, again, there's different models come out with, slight movements of these lines. Okay. Now, one of the biggest, what is causing this uncertainty? And a lot of it, you could say it's feedbacks. Some of these feedbacks we don't understand. A feedback is, when something happens and it causes something else to happen that affects the original thing that happened. Or it's probably better I just give you an example. So a type of feedback is in the permafrost, right? The frozen soils. So if we have some warming, permafrost melts, which releases CO2 and methane, which is locked up in the ice, which causes more warming, which causes more melting. So this is a positive feedback, getting more and more, or something you would call a snowball effect. And we don't understand how much, what increase in temperature will cause what amount of melting, will cause what amount of methane release. And so that's an example of a place of uncertainty when it comes to melting. Another big uncertainty relates to water vapor. So for example, when it gets warm, then you can have more evaporation. Water is a greenhouse gas, so that should cause higher temperatures, more evaporation, right? And this is a snowball effect. But on the other hand, when we have this increased temperature and water evaporates, we could have more clouds that end up reflecting the sunlight, which has a cooling effect on the planet. Okay, that's a negative feedback. So is the warming going to cause this positive feedback or the negative feedback? Our understanding of cloud physics and cloud dynamics is one of the big areas of uncertainty of climate change science. And so that's also. And another one is tipping points. When we do these models, we're modeling the climate as it is right now. However, we could reach a point where there's such big changes in the Earth that we have maybe a reorganization of ocean currents, or say it gets so dry in the Amazon that it just burns up. Well, right now the Amazon has a big effect on the climate, so we would be in a completely different climate if that happens, or if the Antarctic ice sheet just slides off into the ocean. And so we don't know where these tipping points are in our climate system. So all the modeling I've showed you relates to the present climate, right? predicts maybe 6 degrees by the end of the century. But if something like this happens, all bets are off. We could end up with 10, 20 degrees increase. And so that's pretty scary and a big area of uncertainty. And then I'm not going to go through all this, but if you want to say, okay, so it's warmer, how's that going to affect agriculture or forest fires or sea level and fisheries or any kind of infrastructure? All those are big, obviously big uncertainties that scientists are working on. Okay, so we're gonna stop and go for questions, but I'm gonna leave you with one slide here, which is this one. So one of the biggest things you hear people say is, oh, it's been warmer in the past. This is natural variation. And that is true, right? We are here at our temperature. We had ice ages recently. Back in the Cretaceous 50 million years ago, it was 6, 7 degrees warmer. However, consider that if we, by the end of this century, we might be at a temperature that we haven't seen since 50 million years ago. And what's really the problem is how fast we're getting, right? All of our ecosystems, all of our infrastructure, all of our agriculture is adapted to this climate and this temperature, and there'd be no time for that adaptation to take place if we're changing the temperature that fast. So anyone who argues with you about oh, it was warmer in the past, you can say, yeah, but how fast we're getting to that different temperature has never been seen before. The only time maybe was this episode right there, the Paleoeocene thermal maximum. That was a temperature change that happened over about 5,000 years, not 100 years. And we did see massive extinctions associated with it. And we weren't around to have to, deal with it. So anyway, so that's why there's really no debate in the scientific community, just a question of how much warming will happen, what the effects will be, not, is it warming? Will it continue to warm? Okay? Yes, a lot of data.
We'll take some questions, but I have one for all of you first. Something I didn't mention about Andrew is that he's a devoted dad of 2 youngish children, a teenager and a younger than that daughter. Y'all have kids, y'all have grandkids. Y'all are going to say, yeah, this is terrible. Business as usual, I'll be dead. I hear that a lot when I talk to adult groups. It isn't about us per se, although certainly we are impacted by 426 parts per million. I haven't looked at that for several months, and I'm like in despair with that number because it's going up. We're not. So the challenge is think of who in your life you love. Think of who in your life matters to you, who will be around in 25 or 30 or 50 years, and what your hope for their planet would be. And then amp up all the good stuff you're already doing. Y'all are recycling, you are composting, many of you are watching your carbon footprint, you're already doing ride sharing. So I want you to keep thinking about what else you can do, including voting for people who get that this is true. So I'm off my soapbox, and we will open this for questions. Of a phenomenal presentation. I can think of a dozen other places to bring you out. Okay, Zoomers, would you like to ask any questions? And do we have any from the audience? Okay, let's start with Bob, then Laura.
You mentioned uncertainty in the atmosphere, particularly how clouds interrupt the sunlight coming in. How much uncertainty or certainty is there about what is proposed of sprinkling particles in the upper atmosphere to deflect sunlight?
So we do actually have a whole nother lecture on climate solutions, but yeah, so what you're talking about is something geoengineering, which is the idea of actually engineering the temperature of the planet, and one of those ways is putting particles in the atmosphere. And what I tell my students is that it's hard to, even if it were technically possible, it's hard to imagine it ever being done because somebody would have to be responsible, right? So that we don't have a world government. Like say, is one country going to do it? And there's going to be winners and losers, right? Some places, so it might change the average temperature, but it could change, decrease precipitation in some place, increase some place could be flooding. So think of the lawsuits that would be involved there. And so right now, geoengineering is kind of being held as as a back pocket. If we have one of these crossing of the thresholds, and we see just huge, sudden huge increases in temperature. Maybe we pull that out of our back pocket, but it's hard to see that being any kind of a solution, in the world we're living in now. Although technically it worked.
No, oh, okay, yeah, well,
What's the latest on the hole in the ozone layer?
So, okay, so ozone, often people are confused about ozone. Ozone is both a greenhouse gas and, and when it's in the lower atmosphere, when it's in the upper atmosphere, it protects us from radiation. And so it's not really related to climate, the ozone hole is not related to climate change. We kind of solved that ozone problem with the Montreal Protocol back in the 1980s, where we, agreed to stop using CFCs in our spray cans and stuff. And it worked. However, most refrigeration and cooling switched from HFCs to CFCs to HFCs, in other words, which is also a greenhouse gas. And so the Montreal Protocol didn't have any help with the climate issue, but it is a good model for how a big environmental problem can be solved and maybe applied to, climate change. Does that answer your question? Okay.
one of the things I'd like to add to that conversation, though, is that the world did get together with the Montreal Protocol. So we actually have, yeah, but it can be done. We can do it.
An alternative.
Yeah, so our alternative is leave fossil fuels in the ground and suck it carbon dioxide out of the air.
Hi. I'm going to introduce a different concept here. When I started research back in the 70s, population explosion was the big thing. We are going to just keep multiplying and cannot feed all the people and et cetera, et cetera. Now they're talking about population starting to decrease and projecting, I think, by 2100, a real decrease. My question here is this the same kind of phenomenon that could happen with climate? And what is the effect? What would be the effect? There are two questions of the decrease in population to help climate explosion.
Okay, so for the population decrease is happening in developed countries mostly. Right. So as countries develop, as economies develop, population growth decreases. So now the release of fossil fuels is not related to population, it's related to consumption, which is not decreasing. Because again, when you have a developing country, there's more consumption. And so we're not going to solve our problem with decreased population growth. Yeah.
Hi, my question has to do with how climatologists think about nuclear energy, nuclear power plants.
Well, can I speak for all climatologists? No, so as a geologist, I don't think I've ever met a geologist who was against nuclear energy. I think a lot of scientists are for nuclear energy. I think that, of course, the concern is, the radioactive um, waste from it. Um, I think that we've got good geologically stable places to put it. But I know that's not, everybody's opinion, but I think what's more important right now is the climate issue compared to the nuclear waste issue. But someone can argue with me. What do you think? Bill Gates is pro-nuclear? Can you find this on YouTube? Bill Gates talks on storing nuclear waste. Yeah. Yeah, I do too. Although, of course, fusion would take care of that problem, but we don't have that yet. So, yeah, we should all look, but of course, that's more of a political question than a technological question at this point.
There's such a thing as international polar years, international geophysical years, where scientists have accumulated data worldwide simultaneously and shared it. How knowledgeable are you about this, and how does that data contribute to climate?
Uh, Not knowledgeable. No, I don't know about the specifically International Geophysical Year data, but we're drilling ice cores all the time. I mean, this kind of climate research is happening all the time. Yeah, I'm not aware of the importance of those specific years. But one more.
Just a point on that nuclear energy, it's as long as we haven't solved the nuclear war issue, the nuclear plants are a hell of a target and could magnify the effects of a nuclear war dramatically. So that we've got to solve that first problem first, I think.
You think a nuclear power plant's a bigger target than New York City? Yeah, it could be the case that, but we have nuclear power plants. It's not like building more of them is going to be more of a target, right? So,
Zoom folks, do you have any questions? You've been unusually quiet today. Nothing in chat. Okay, well, I'm glad nobody had any complaints about sound today, so thank you. That's real progress. Andrew, thank you. It's a tremendous amount of material presented really clearly. And I think, yeah. Yeah, well, I guess you got good at it, right? Practice makes perfect. Just one comment about nuclear plants. They are a solution. If you're going to build new ones, they take 15 to 20 years to permit and build, and we don't have 15 or 20 years anymore. If we'd started 30 years ago, we would have, but we don't. And I do want to make one addition to the who thought of the impact of carbon dioxide first? Oh, yeah, that's right, Eunice Foote, and I like to tell the story because she was a scientist, as was her husband, and she was the very first one to theorize. And I loved how you broke out how the evidence is different kinds of evidence. She theorized that by burning coal, we were going to put carbon dioxide in the atmosphere and the atmosphere would warm. And she wrote a paper. But women were not allowed to present papers to the National Academy of Sciences. Her husband presented it on her behalf, and it was before 1859. I'm sorry, I don't remember the year. I just thought I would throw that in. Well, okay, then we'll have to research that. So I don't want to be speaking incorrectly. Yeah. Okay, well, we'll go back to our footnotes and double check it. Are there any closing comments for the series? This is the last of our whole shebang. You guys have been amazing with absorbing a lot of information and not giving up. Yeah, you've forgotten it all. It's okay. They're on YouTube. By the way, the program is on YouTube, and I'll make sure you get a link to that so you can see that. Eventually, it'll get on YouTube, right, Pam? Right. Okay. And so next week, something interesting is happening. Let me just repeat. It'll be 1:30. It'll be, I believe, here, and it'll be a movie with a discussion following Sinking Cities. And we thank Don Smith for that. And everybody can stop bringing me your plastic. Thank you, Kristen. And you can put it in your own boxes. You know, I have to talk to Don. It's pretty long.